In this video, I'm going to talk about Thevenin Theorem. Thevenin Theorem, Norton Theorem, Maximum Power Transfer Theorem, all these three theorems comes under the same category. As long as you understand the Thevenin Theorem, the rest of the two are almost similar, just a few extra steps are added. So I'm going to start with a simple example. Here in this example, he's asking about find current in 5 ohm resistor. The 5 ohm resistor is right here by using Thevenin theorem. I'm going to solve this example in 4 simple steps. So step 1, always remove that resistor. Okay, wherever we need to find the current or voltage or power, remove that resistor and label the terminals as A and B, as I mentioned here. Okay, our final goal is transferring this big circuit into a simple equivalent circuit looking from the AB terminals with a voltage source in series with a resistance. The voltage source called Thevenin voltage, resistance is called Thevenin resistance. Thevenin is a person name who invented this theorem. So in step 1, we remove the terminals, we remove the element and label the terminals. Sometimes some circuit you will not have any element right there, saying that they might say find the Thevenin equivalent circuit between AB terminals. If that is the case, we don't need to do step 1, it is already in there. Now step 2, our goal is finding VThevenin. VThevenin is nothing but VAB, which is VA minus VB. Okay, our goal is finding VAB in this case. Now, how do you find VA? This is a simple circuit. I can clearly see by using the voltage division rule, I can find it. Or I'm going to ground this here. Or I can say I can find the current here, 30 divided by 6 plus 6, which is 2.5 ampere. Now, my VA is going to be voltage drop across this, or I can use the voltage division rule. Anything will work. So I found VA as 15 volt. Now I'm going to find VB. VB is nothing but voltage between this and the ground. Okay. Usually whenever we say voltage at any point VA, we are talking the second point as a ground. So VB equal to, how I did, current times the total resistance. The total resistance is 3 plus 2. These two are in series. So 5 ampere times 5 ohms, that will give me 25 volt. So my VAB equal to VA minus VB, 15 minus 25, that is minus 10 volt. Now step 3, find Orthovinion. Okay, the important point while finding Orthovinion, replace all independent voltage sources with short circuit and independent current sources with open circuit. That's an important point. So why do we need to replace it? Our goal is finding the resistance of the circuit between the AB terminals, and the independent voltage source always have zero internal resistance. Ideally, practically there is always some internal resistance, but ideal case it always has zero internal resistance. Same thing with the independent current source, it always has a infinite internal resistance. So independent current source we always open circuit, or we always replace it with open circuit, and independent voltage source we always replace it with short circuit. Now we're finding the resistance between AB terminals here. So start walking from A, reach the B. So if you look at here RAB, so start walking from A, here is my A, and then it is splitting into 2 parallel paths, 6 ohm and 6 ohm, those two joining right there, point C, and then it is going to 2 ohm and 3 ohm, and then you are reaching B. So basically 6 parallel, so I label them as R1, R2, R3 and R4. So R1, R2 parallel, and then the parallel combination is series with R3 and R4. 6 parallel with 6, Usually this resistance value is 6 divided by 2. So two equal resistors are in parallel, then the final resultant resistance is resistance value divided by number of resistors in parallel. So 6 divided by 2. So if you have 6 parallel with 6 parallel with 6, then 3 resistors are in parallel. 6 divided by 3, that will give me 2 ohm. That's a shortcut when the resistors are in parallel. So this is 2 ohm plus, my apologies, 6 divided by 2, which is 3 ohm. 3 plus 3 plus 2, which is 8 ohm. That is the total resistance. That's Orthovinion. Now step 4, connect it back, Thevenin and Orthovinion. This is simple circuit. Now connect back your 5 ohm resistance where we removed in step 1. Connect it back and now find whatever he's asking for. So Thevenin end up with negative 10 volts. That means probably current is flowing in the opposite direction. Okay, so B must be positive and A must be negative. So 10 divided by 13, which will give me 0.769 ampere. Here is second example. I'm doing the same example what we did in the first case, but this time I'm trying to find the current passing through 2 ohm resistor. So 2 ohm resistance is right here. Trying to find the current passing through 2 ohm resistor by using Thevenin theorem. So as usual, I'm going to follow 4 steps. Step 1, remove that resistor, label the terminals as A and B. Okay, that's what I did here, A and B. Now step 2, find VAB. VAB equal to VA minus VB. Here, since there are 2 sources, what I'm going to do, I'm going to use nodal analysis to find VAB. B is going to be grounded, so VB equal to 0. So as long as I find VA, that should be good enough. Now, while finding VA, here, look at this 2 ohm resistor. Basically, nothing is connected. It's just you're connecting your extension cord to the wall, but nothing connected to your extension cord. So there won't be any current passing through it. But at the same time, whatever the voltage available here, it will be available there. So as long as I find the voltage at this point, VA, that is my Thevenin. So what I'm going to do at VA, apply KCL. So I'm going to take IA, this is my IA, IB and IC. So IA plus IB plus IC equal to 0. IA equal to VA minus VX. I'm sorry, I think I took this as IA. VA minus, I'm sorry, I'm showing you a different node. I'm applying KCL at VA, right? So here is my IA, here is my IB and IC. So IA equal to VA minus VX over 5. So I'm applying KCL here at VA one more time. And IB is nothing but negative 5 ampere and 0. So if I simplify, that value is VA minus VX equal to 25. This is my equation 1. Now at Vx, apply KCL. At Vx, I'm applying KCL. I'm taking this current as I1, I2 and I3. So I1 equal to Vx minus 30 over 6 plus I2 equal to Vx over 6, I3 equal to Vx minus Va over 5. Okay. After simplifying this equation, we end up with minus 6 Va plus 16 Vx equal to 150. That is my second equation. So these two are the main equations. Now what I did here, I multiplied equation 1 with 6. So it will become 6 Va minus 6 Vx equal to 6 times 25, which is 150. And the second equation I have minus 6 Va plus 16 Vx equal to 150. I'm adding those two equations. So 6 Va minus 6 Va get cancelled out. 16 minus 6, 10 Vx equal to 300. Based on this, I end up with Vx equal to 30 volt. And I substituted Vx in the first equation I end up with finding VA equal to 25 plus Vx, which is 25 plus 30, which is 55 volt. That is my step 2, finding Thevenin. Now step 3, finding Orthovinion. Here same thing, like similar to the previous case. Replace the voltage source with short circuit, replace the current source with open circuit, because the internal resistance of current source is infinite. That is the reason. So same thing here, start walking from A, reach B. So if I redraw the circuit, I'm going to start walking from A, 3 ohms, and I see 5 ohms, and then I'm going to reach, say, here point P. At point P, separating in 2 paths, 6 ohm, another 6 ohm. Now they're joining at point Q, and Q and B are the same points. So based on this, 3, 5 are in series. The series combination is also series with the parallel combination of 6 and 6. So 8 plus 3, I mean, we know that this resistance value is 3 ohm. That value is 11 ohm. Now the final step, step 4, we have the Thevenin, Orthovinion. Now connect back the 2 ohm resistor which we replaced, and that will give us the current passing through the 2 ohm resistor. Here that current is 4.23 ampere. Now why do we need to do the Thevenin theorem, since we already know mesh analysis, nodal analysis, or other theorems like superposition or source transformation? The main advantage with the superposition theorem is, say a simple example, you're building a radio circuit. Okay, the radio circuit will have at least 100 elements. Okay, if it is 100 elements, there might be like 20 loops or 20 nodes, and you found an error with a small element right there. Probably that could be a resistor. Okay, you found noise is coming from your radio because of that particular resistor. What are you going to do? You're going to replace that resistor and find other parameters, how the system is working, like current flowing through each element or current passing through that. Okay, in that case, what are you going to do? You're going to replace with 4 ohm, 5 ohm, 6 ohm different resistors, and you need to solve the circuit that many number of times. Depending upon how many number of times you replaced your resistor. So instead of solving that circuit so many times, what we're doing, we're trying to find the equivalent circuit of this radio between these 2 terminals. So now it is easy for us to replace the resistor so that we can find the current or energy or power consumed by the resistor. Okay, thank you. I'll stop this video here. In the next video, I will explain, I will solve one more Thevenin theorem, and then I'll move on to the dependent sources. Thank you.